All right, Summer Physics 3-4. We're on to our day 14 lesson. Just one more day left in this course. And this is on the subject of wave properties. So what is the superposition of waves? So when two waves occupy the same space, they are said to be superimposed, and this is called superposition. And this is a unique property of waves that doesn't exist with matter. Matter, you can't have two different soccer balls occupying the same space at the same time. But waves, two different waves can occupy the same space at the same time, and that's called superposition. So there you see a red wave right there, and down below you see a yellow wave. Now when two waves are superimposed, the amplitudes, heights of the waves are added to each other. So there, what happens is, if you assume that that yellow wave and that red wave are occupying the same space, I'm showing them separate so that you can see that they're two different waves, but if you assume that they're occupying the same space, then what you do is you add the amplitude. So you see the amplitude, the highest point of the red wave, and you see it's lined up with the highest point of the yellow wave, so you add those together, and you get that blue wave down below. That's the resulting wave. And the highest point of that blue wave is the addition of the highest point of the yellow and highest point of the red wave. So the maximum amplitudes of the two waves here are in the same place. These waves are said to be in phase. So let's see this, the same thing, but let's see them when they're placed on top of each other. So there's the yellow wave. You place the red wave right on top of it, and you get that blue wave. And that's superposition. So this is called constructive interference because it actually builds the wave. It sounds funny that it's interference, but that's what the term is. It's constructive. It actually builds the wave. It makes it bigger. It makes the amplitude higher. And these waves are said to be in phase when they do this. When the tops of one wave lines up with the top of another, they're said to be in phase. So when two waves are out of phase, they can cancel out and result in an amplitude that is less than the amplitudes of each of the waves. So there's the amplitude of +3 of the red wave, same wave as on the last slide. And there's the yellow wave, same wave as on the last slide, but you can see that the top of the red wave lines up with the bottom of the yellow wave. It should be exactly lined up in that image. So what they're going to do is they're going to cancel out. Just like +3 - 3 equals 0, these two waves are going to cancel each other out at that point and at all other points. So when the waves are added, the result is an amplitude of 0. So you can see that that wave down on the bottom, it's flat. It's flat along because every point along those two waves, the red and the yellow wave, they're canceling each other out. So that means if you have two light waves, both of them look like light. You can see the light in each of those lights, but you have the waves exactly out of phase. They'll cancel each other out and you'll have dark spots. And I'll demonstrate this in class with sound waves. So this is called destructive interference. And these waves are said to be out of phase. What is refraction? Just as you can run faster in air than you can in water, a light wave moves faster through air than water. When a light wave going through the air hits water, the side of the wave that hits the water first will slow down first. This causes the wave to bend in that direction. When light bends because of this kind of a change in medium, it's called refraction. So here comes a light wave through the air. In the direction of the wave, it's heading to the water. And you can see how the bottom part of that wave is hitting the water first. The top part isn't going to hit right away. So you can think of it like a car where one wheel, with the wheel on one side of the car go into the sand. It's going to cause the car to swing around. All of a sudden the wheels in the sand are going to stop. So what's going to happen is that top side is going to swing around like that. So this side, the side that you see pointing to there, of the wave hits the water first, so the light refracts in that direction. Okay, so that causes light to bend. An example of this would be sticking a pencil in a glass of water, and if you look at the pencil from certain angles, it looks like it's bent or it's broken or it's in two different places, and that's because of the refraction of the light. What is diffraction? When light passes through an opening, like a little hole in a piece of paper, it bends by the process called diffraction. The longer the wavelength is compared to the width of the opening, the greater the diffraction. So there's a shorter wavelength, it's going to have less diffraction. There's a longer wavelength, it's going to have greater diffraction. It bends more. So light can actually bend going around a corner or through a hole in a piece of paper. It's kind of an odd characteristic of light, but other waves can do this as well. Okay, what is polarization? Polarization means that only waves oriented in a certain direction, that means pointed in a certain direction, can pass through a barrier. Glass can be polarized so that only some of the light can pass through. Below, only the light wave oriented up and down, this one, can pass through the glass, like that. The sideways light wave, this one, is blocked. Think of a couch going through a door. So if you have a couch, or maybe you call it a sofa, and you want to get it through a door, you can't get it through lengthwise, so you got to turn it up on its end and then push it through the door when it's turned up and down on its end. And that's an example of this. It has to be oriented or pointed in a certain direction in order to get it through this glass, just like getting the sofa through the door. What are sound waves? So we've talked about sound waves. Sound waves, as sound comes out of a speaker, it produces a longitudinal wave that causes the air molecules to press together and then be released in alternating high pressure, low pressure areas. This is the same pattern as a spring. So there you see a speaker down below, and as it puts out vibrations in the air, it causes the air to bunch up, and then it spreads out. You can see the areas of high pressure where the air molecules are bunched up, and then low pressure where they're spread out. And that causes the wave to travel through the atmosphere into your ear where you can hear it. Now the molecules over by the speaker are going to stay by the speaker. They're not going to go across the screen there. They're just going to bunch up and release. Bunch up and release. Similarly, the molecules over on the right side next to the arrow that says wave direction, they're going to stay in that place. They're just going to bunch up and release. Bunch up and release. So that's called a medium, and that's how air molecules can carry a sound wave through the air. What is the Doppler effect? So a moving train sounds its horn. The train is moving into the sound wave that goes out in front of the train. This squeezes the wave in front of the train. The train runs away from the sound wave going out the back of the train. This stretches this sound wave. So you notice the sound wave coming out the front is shorter, has a shorter frequency, and shorter frequency means higher pitch. Longer, or shorter wavelength, I should say, means longer pitch, means higher pitch, and longer wavelength means lower pitch. So in other words, the sound is going out in all directions at the same speed, but the train is chasing after the waves that are going out the front. So it's tending to shorten their wavelength, whereas the waves going out the back are being stretched out. And so what that does is it means the train comes by at a higher pitch, and then as it passes by you, it seems to go to a lower pitch. And I'll play a video that will show an example of this. Beats. Beats, when two sounds of different frequencies are heard together, the sound alternates between loud and quiet. Sound waves can be added to one another and can subtract from one another just as transverse waves do. So you'll notice you have two waves there, two sound waves of different frequencies, different wavelengths. Now, they both are at their high amplitude point where you see it says loud on the left side, so that's going to be louder. And then where you go over where it says quiet, you see that one of them is at a high amplitude, that is the air molecules are bunched together, and the other one is at a low amplitude. That means they're spread out. So they're going to tend to cancel each other. So that would be quieter. And then you go back to a little further to the right, and you see that the high amplitude on both of them is in the same place, so that's going to be louder. So it's going to kind of, even without raising or lowering the volume or the sound, it'll make it sound like it's being lowered and raised. So the quiet, where it says quiet, that's destructive interference. Where it says loud, that's constructive interference. Okay, and the frequency of beats is very simple to compute. You simply take the two frequencies and you subtract one from the other. Absolute value means you're just always going to come out with a positive number. So if it was 4 minus 2, it would be 2. If it was 2 minus 4, which equals negative 2, it would still be 2. It's always going to be a positive number. The frequency of the beats has got to be positive. The absolute value symbols mean that the answer is always positive. What is the beat frequency of a 340 hertz and a 360 hertz wave? So you simply say 340 minus 360 and you take the absolute value and that gives you 20 hertz. So what is the beat frequency of a 400 hertz wave and a 250 hertz wave? 400 minus 250 equals 150 hertz. So that's what beats are, and I'll show you an example of that on a video in class as well. Alright, so that takes care of our final lesson on waves, and we'll do a couple little projects with waves, and you'll be able to see some real world examples of how they work.